Hello my dear students, myself Swati from Department of Statistics. So in this video we are going to discuss Statistical Quality Control Unit 2. So the topic is construction of control charts for attributes. Many quality characteristics are not measured on continuous scale or even a quantitative scale. In these cases, we may judge each unit of product as either conforming or non-conforming on the basis of whether or not it possesses certain attributes, or we may count the number of non-conformities, that is defects, appearing on a unit product. Control charts for such quality characteristics are called control charts for attributes. And the control charts for attributes are classified into control charts for fraction defectives, and second one is control charts for number of defectives, and the third one is control charts for number of defects per unit. In this video, we shall now discuss one of the control chart for attribute. So that is the control chart for fraction defectives. So this can be represented as small p chart. So now construction of control chart for fraction defectives, or this chart is also known as proportion defectives chart. So and this can be abbreviated as P chart. While dealing with attributes, a process will be edged in statistical control if all the samples or subgroups are ascertained to have the same population proportion capital P. So if D is the number of defectives in a sample of size small n, then the sample proportion defective is small p is equal to D divided by n. Small p is equal to D divided by n. Hence, the number of defectives follows binomial distribution with the parameters n comma p. So then the expected value of D, so that means NP, and the variance of D value is NPQ. So here Q is equal to 1 minus P. Now we have to find out the expected value of P and variance of P. Now expectation of P is equal to, so we have to substitute the value of P is equal to D divided by N here. So now the expectation of P is turned into expectation of D divided by N. So here we are using the expectation of property, that is expectation of AX is equal to. Here A is a constant and X is a variable. Then expectation of AX can be written as A into expectation of X. Then here 1 by N is the constant value. Here we are taking the outside to the expectation, then 1 by n into expectation of D. Now you have to substitute in this relation the expected value of D, that is NP. 1 by n into NP. We get the value is here capital P, and variance of P is equal to. So now you have to substitute here the value of P here, that is D by N, variance of D by N. Again here we are using the variance property, that is variance of AX is equal to A square into variance of X. So based on this variance property, variance of D by N can be written as 1 by N square into variance of D. So now you have to substitute the value of variance of D here. So that is NPQ. NPQ divided by N square. We get PQ divided by N. So again you have to write down Q in terms of P. That means 1 minus P. Now we get the value of variance of P is P into 1 minus P divided by N. Now set up the control limits for P chart. The 3 sigma control limits for P chart are given by UCL is equal to expectation of P plus 3 into standard error of P. So expectation of P is capital P plus 3 into standard error of P, that is the square root of P into 1 minus P divided by N. And the central line CL is equal to expectation of P, that is equal to capital P. And the lower control limit LCL is equal to expectation of P minus 3 into standard error of P. So that is equal to capital P minus 3 into square root of P into 1 minus P divided by N. So these are the 3 sigma control limits for P chart. So coming to the P chart for fixed sample size. Suppose we have to take k independent samples of each of sample size is fixed, that is small n, from the given production process. In the ith sample, the number of defectives can be denoted by di. Then the fraction defective Pi for the ith sample is given by Pi is equal to di divided by n. So that means the number of defectives in the sample divided by the size of the sample. So here we have to study two types of cases. When the standard is given value, when the standard is not given. So first we have to discuss first case 1. So in this case the standard value is given. So the standard value of P chart is here capital P. So this value is given value. So the given value of capital P is here. We have to say that this value, that is P dash. Now we have to substitute this P dash value in the 3 sigma control limits for P chart. Then UCL is equal to P dash plus 3 into square root of P dash into 1 minus P dash divided by N. CL is equal to P dash. LCL is equal to P dash minus 3 into square root of P dash into 1 minus P dash divided by N. So this is the first case 1. And coming to the case 2. So here the standard value, that is capital P value is not known. So that means capital P value is unknown value or not given value. Then the capital P value is replaced by its unbiased estimator, that is P bar. So then the 3 sigma control limits for P chart for fixed sample size are the upper control limit UCL is equal to P bar plus 3 into square root of P bar into 1 minus P bar divided by N. The central line CL is equal to P bar and the LCL. So that means the lower control limit is equal to P bar minus 3 into square root of P bar into 1 minus P bar divided by N. So here the value of P bar can be obtained by the total number of defectives in the K samples divided by the total number of units in the K samples. That means small p bar value is equal to total number of defectives in the K samples can be represented as summation D divided by total number of units in the K samples. So that means summation N. So by the simplification we get the value of here summation Pi divided by K. So in the calculation of P bar we are using this formula or this formula. So this formula is summation Pi values divided by K. So where Pi is equal to, already here we have to write down Pi is equal to Di divided by N. So the number of defectives divided by N. And the construction for fixed sample size. So in P chart we take the sample number along the horizontal scale, that means x-axis, and the fraction defective values. So that means Pi values, P1, P2 and so on, Pi and so on, Pk values along the vertical scale, that means y-axis. the sample fraction defectives P1, P2 and so on Pk values are plotted against the corresponding sample numbers as points, and the central line is drawn as a dark horizontal line at P bar, and UCL of P chart and LCL of P chart are plotted as dotted horizontal lines as computed. And coming to the P chart for varying sample sizes. Here we have to take random samples of different sizes, that is N1, N2 and so on Ni and so on Nk from the given production process. Then we shall obtain different sets of control limits for each sample, although the central line remains the same at P bar for all the samples. So such limits are known as varying control limits. So in this varying control limits, the case 1, so that is when the standard is known value, that means here the standard of P chart is capital P. So this capital P value is known value. Then we are writing the 3 sigma control limits for P chart. So those are UCL is equal to, so known value of capital P is, we are denoting P dash. So you have to substitute P dash value in these limits. Then we get UCL is equal to P dash plus 3 into square root of P dash into 1 minus P dash divided by Ni. And the central line CL is equal to P dash. And the lower control limit LCL is equal to P dash minus 3 into square root of P dash into 1 minus P dash divided by Ni. And next one is case 2. So here the standard, so the standard of P chart is capital P. So this P value is unknown value or not given value for unequal samples. So here the sizes are different, unequal sample sizes. So the standard P value is not given value. Then the 3 sigma control limits are UCL is equal to P bar plus 3 into square root of P bar into 1 minus P bar divided by Ni. CL is equal to P bar and LCL is equal to P bar minus 3 into square root of P bar into 1 minus P bar divided by Ni. So here the value of P bar can be obtained by, so total number of defectives in the K samples divided by total number of sizes in all K samples, that is a summation Ni. So we get P bar is equal to summation Di divided by summation Ni. Construction for varying sample sizes. In this P chart, we take the sample number along the horizontal scale, that is x-axis, and the statistic P. So this means fraction defectives or proportion defectives along the vertical scale, that is y-axis. The sample fraction defectives, those are denoted by small p1, small p2 and so on small pk. So these values are plotted against the corresponding sample numbers as points. The central line is drawn as a dark horizontal line at P bar. So in this case, since the size is changing, there will be one LCL point and one UCL point for every sample. Hence, the lower control limit and the upper control limit are not horizontal lines since they are changing for every sample. Then the control limits are known as moving control limits. Interpretation: if all sample points fall between upper control and lower control lines and not showing any specific pattern, then we say that the production process is under a state of statistical control. Otherwise, we say that the production process is lack of statistical control. Particularly, if the sample points fall above UCL, so those points are known as high spots, then the quality of the process is declining or deterioration. So reasons for this should be traced and eliminated. And particularly in the second point, if the sample points fall below the LCL line, that is, those points are known as low spots. So that means then the quality of the production process is an improving, but not at up to the level. Reasons for this kind of low spots is should be looked for and incorporated into the process if possible. And the next point is if the points fall both above UCL and below LCL, then new samples are reconsidered.